Yeah, hello all. I think let's start with this week's. Even before going that, I think in this week we are going to solve this undirected graph-based models. So I'll quickly go over some basic things just to recap before we solve. Uh, let's say if we are given a factorization. Let's say if we are given a graph, say x1, x2, x3, x4, right? X5, x6. Yeah. So now this is a function of six random variables, right? So how do you represent this for an undirected graphs? Basically, what we do is we take the cliques in the graph. Cliques is nothing but the maximal connected subset of the graph. So in this thing, we have a clique like x1, x2, x4, x2, x4, x3, and x3, x5, and x3, x6. Right. So that is some function of, let's say, phi one of your x1, x2, x4, and phi 2 times x2, x3, x4, and phi 3 times 3x5, phi 4 times x3, x6. Right, so you multiply these things. So this expression, right, is represented by this graph, right? Now, uh, so if we have, say, something like this, x1 and x2 and x3, right here, this thing is represented by product of two factors, that is phi1 of x1, x2, phi2 of x2, x3, right? So we wanted to know uh, conditional dependence, independence of this, let's say, these three nodes. We'll come to this graph in a bit, in a moment, right? So whenever you express something like this, right, x1, x2, x3 as a function of x1, x2, and x2, x3, then you have this property, right? x1, x3 given x2, x1 and x3 are conditionally independent of x2, right? That means you can write like this. Sorry, p of x3 given x2. Okay. Now Yeah, what happens is once you know, once you are given this thing x2, right, and you want to view the function only uh, as a as a dependence on x1 and x3, right, provided your x2 is fixed to some value, right, then it is as good as, right, removing this node from this graph, right. So here you have this two independent nodes, right, they are independent given x2. So whenever you have, let's say, x1, you have some path, if a path is blocked by some node, right, then the the other nodes are independent once you see that node, right. So in this case, right, if I have given x3, right, then this holds x1, x2, x4 are independent. Typically you represent independence by like this, right, independent of x5 and x6, right. Yeah, so mostly we will use this property only in today's problem solving session, right. So it is clear, is that clear?
In the above diagram, which one was x2?
Can you come again?
In this diagram, which is x? Yeah, is that x2?
This
Because
is
2
x4.
times it's x1.
No, this is x4.
On top of x4,
X2.
that's x2.
Yeah, right. So whenever you see that, in especially in undirected graphical models, whenever you condition on, let's say, x2, you can remove that and all the edges connected to that. Then, so yeah.
Could you please summarize this in one statement? What was the I missed actually due to network?
So
How do you summarize this?
so basically, here we have discussed the independence notion of independence in undirected graphical models. So if you have a set of nodes, let us say some set of nodes here, right? Nodes. You call this as set X, okay? And you have another set of nodes, set Y, right? Some nodes. Not just two. This just for presenting. I'm doing two. They can be any. And you have some other set of nodes, right? Now here there can be any connections from X to Y, and all the connections from X to Z are passing through Y, let us say, right. Then in this is very general scenario, okay. In this context, whenever you see Y, right, that makes X and Z independent, right. This is what I wanted to convey. This is a bigger picture, okay. This thing,
Okay.
right. So all the trails is a path from X to Z are by the set of nodes in Y, if that holds, and whenever you see Y, right, this set of nodes you see, that makes X and Z independent. So this is the bigger statement. So
Okay.
it is simpler, much simpler than the directed. If you remember directed, we have arrows and we had this three uh, things, right, to decide dependence or independence. In undirected graphs, it is very simple.
Yes.
And yeah, I think this is the only main thing I wanted to say. If time permits, we'll try to prove this part. for a simple case, right? Just x1, x2, x3. And yeah, I think that's it. Let's go and solve problems, right? Yeah, so this is the first problem, and this is the graph. And which nodes are conditionally independent of each other given B? You have given, you have seen B. Provided this information, which nodes are independent? You can just follow just whatever I have said and try to answer D. So no, D is not the right option because you have a path from A to F that is dependent by C, right? So none of the options are correct here. Just if you remove B and all its no all its edges, right? Now in all these options you can find a path. So A to D, A can reach through D like this. A, C, E, and D. D and D anyways they are connected. C and D, C, E, D, A, F, A, C, F, right? So that's the thing. And
Okay, so there has to be a path between the nodes.
you should not have any path. If you want independence, there shouldn't be any path.
Then A and F, there is no path via B, no?
Which one?
A and F, there is no path via B, no?
No, it's not about B. Well, let's try to. If you remove B, right, all these edges will be removed, right? A, B, E, B, C,
Correct.
right? Now you can reach to F through A, through C, A, C, and F, right?
Yes.
Yeah, it will be clear when you see the next example. Right? So yeah, I modified this graph, and same thing. You have seen B, uh, right? Now, which of the nodes are independent? Just remove the node B and all its connections. This are C and D. C can C reach D without B? No, right? So C and D are independent. D and D, they of course they are dependent. Right? E and C, even E and C cannot reach if you remove B. A and F, anyways, they reach through C, right? So option A and option C are the correct answers, right? So is it clear now? The judging independence, deciding independence in the undirected graphs.
Yes.
Okay, so in this graph, how many uh, terms will be there in its potential function factorizations? So potential function factorization is nothing. I mean, let me try to do this. A, B, C, D, E, F. Right? Okay. So right, we have A, B, C, D, and this connected. Right. So basically, um, so any factorization, right? You in undirected graphical models, especially right x2, so on xd, let us say, or xn something, right? Now this is proportional to your uh, set of functions, say phi c of xc. You multiply this over c, right? And this need not be a probability function, right? When you normalize this, you will get a probability function, right? This phi's are nothing but potentials. So typically these are considered to be the cliques. Cliques is nothing but the maximal connected subgraph in a graph. And x is nothing but a subset of nodes, any subset of this x1 to xn, right? So why do we consider maximum cliques while doing this? So in this there are three maximal cliques, right? This part aeb aeb, because these three are connected, fully connected, right? Every node is connected to every other node, so that's what I meant. And another one is abcd, right? Even this is every node is connected to every other node, abcd, right? And another one is dcf. So you have a function, potential function 1, potential function 2, and potential function 3. Now my question is, you can also factorize this as a times e and e times b, right? Why only we consider phi 1 of aeb, right? So just to answer that question, we don't want to assume any more dependencies, any more assumptions on independence. So if I write this as aeb, right? If I write this as say psi of a comma e and psi 1 of a comma e and psi 2 of e comma b, right? So why do we consider this, and why not this is, in this factorization we have an assumption that a and b are independent given e, right? So just that's what we discussed. So if you remove uh, um, I mean condition on everything else, right? A b c d e f, right? Now if you only consider this subset of graph, so you have this thing, this independence a and b given e, provided you have of course seen everything else, right? So that's the reason. So just to answer this, we consider the maximal cliques uh, in your potential functions. So in this example we have three maximal cliques, so that's the thing, right? So your answer is b. And yeah, so HMMs are typically used in the machine translation and speech recognition. So yeah, I mean it's not a, um, so I'll just uh, give you an overview of what HMM is, right? In HMM you have say H naught, which starts some process, right? This at time 0, at time 1, at time 2, at time 3, at time 4, let us say, right? Now this transitions to some state at time 1, and this gives you some observation x1, right? Again this transition at time step 2, h1 will transits to h2, and you have some observation x2, and so on, right? And x3. So this is a directed graph. You have x3 and so on, right? So this is a hidden Markov model. So in many applications, what you observe is x1s, x2s, x3s. Given this x1, x2, x3s, you have to infer what uh, h's are, right? So that's a typical inference problem in HMMs, right? So yeah, it's a big topic in itself, right? So may not have that much time to discuss. Um, yeah. So yeah, just now I told HMMs are used to find the most probable hidden states given the observation sequence. That is D, and probability of a given observation sequence. That even that can also be found out. And yeah, so so this is a Markov chain, and what was asked is what is the most efficient way of eliminating the variables. If you want this, uh, want to compute this thing, right? This event, right? Probability that E takes a value of E, and what is a efficient way to compute that? So let's see. Let's start. There's A, and there is B, and there is C, and this is D. So this is a Markov chain actually. Um, all right, so we want this event probability of E. So how do we do this? E of A, B, C, D. E takes a value of E, and you sum over all possible values of A, B, C, D. Basically, you marginalize them, right? And if you remember the way you factorize these things in directed graphs, right? So this is nothing but node and node given its parent, right? So in this case, P of B given A, P of C given B, P of D given C, and P of E given D, right? Yeah, and we want to sum over all A, B, C, and D, right? So the efficient way, if you see, right, it is this in this order itself, because um, you don't have to what should I put? How should I put it? Condition many variables. So if we condition C, right, you have to take care of both B's and D's here, right? So that's the reason. So this is, let's do this, sigma A, P of A times um, P of P given A, right? And this you have to do it, and then sigma B times P of C given B, right? And then, so I can do this, mass C times P of B given C, and sigma D times P of E given B. So this, the first expression is nothing but P of B, right? So, and on top of this, you have P of C given B. Right now, this expression will simplify to P of C, right? And finally, P of T given C, you have it from this place, right? P of T given C, and when you sum over C, you get P of D. Finally, you have this thing P of E given D, and you sum it over D. Right? This the last summation. You get P of E for a particular value of E, right? So yeah, so efficient way of eliminating is A B C D B. You just have to worry about one condition and not multiple values of condition. Yeah, this you have a better. You can look at once I upload it. Um, yeah, so typically tree widths are defined as the maximal, number of nodes in the clique, right? So in this, there are only uh, there are cliques of width two, right? So the tree width is two. Um, yeah. So yeah, when uh, discussed belief propagation, I think there are. It's typically used for finding the conditional marginals. So probably we'll do it in the next week's lecture if there are any problems associated with this thing, right? So I think we have reached end, right? So yeah, the main today's main takeaway would be this: understanding the independence and dependence in the undirected graphical models, right? So I hope that's clear how to identify them, right? So yeah, if you have any questions from my side, it's done. But if you have any questions, please ask. I'll try to explain. Yeah, if you guys don't have any questions, I think we can stop here. Um, okay. Yeah, and sometime back, guys were discussing right some previous questions. If anyone has it, we can try to solve them. Right. Uh, okay, guys. Then I think we are done for this week. If you guys don't have any questions, so I'll be signing off.